So in this experiment, we'll be extracting Carvone from caraway seeds. You can extract Carvone from other things, but in caraway seeds there's one dominant isomer, stereoisomer, so either the R or the S. But you can extract Carvone from other things, and particularly you can extract the S and the R from different things. So we're going to do a solvent extraction, and basically what you're going to do is just soak crushed seeds in solvent and then extract it out, remove the solvent, and mostly what remains is caraway seeds. Now there are other things in the caraway seeds, and so you may pick up some of those on the IR, and I should put GCMS. And so we're going to actually characterize whether or not we have the R or the S. So you have Carvone, you have the different stereoisomers, and so which one is R, which one is S, and which one is coming from the caraway seed. So you would look up the information about Carvone like you normally do, but we'll look at whether you have the R, S, whether you get a positive or a negative rotation on the polarimeter. So the polarimeter is the only thing that will help us tell this information. We'll use IR to look at functional groups. We'll look at the GC mass spec to look at structural information, and later on we'll look at NMR data. But the polarimeter is the best thing to look at whether you have R or S, and the refractometer tells us a little bit more about the purity of our sample, because there's a refractive index associated with Carvone, and if your number is a little bit off, it's not as pure. Now we're extracting and not purifying, we're just extracting, so there is probably other compounds in your sample. So we're going to be extracting, so you're essentially going to not dissolve, but yes, you're going to dissolve. So you're going to have your caraway seeds, which you crushed in a mortar and pestle. And so you're going to crush it up as best as you can, put it in the solvent, and you're going to let it sit covered for a period of time. Once it's done, you're going to filter it out, and once you filter it, we'll rotovap. Now there are other methods of doing this, but before we go on, we're going to be using diethyl ether. There are greener solvents that we could try, but one thing I want to say is diethyl ether evaporates fairly easily and fairly quickly, so be careful not to inhale it. Do everything in the hood, but then when you're done and letting it sit, make sure everything is covered so that the diethyl ether does not evaporate, because it will evaporate very easily and very quickly. And so after we rotovap, we'll do our analysis of our sample. You're going to get weights and things like that. There are other methods that we can extract Carvone, and I've done a couple of these. So we can use dry ice, and so basically with the dry ice, you take a tube that seals, you put it in, there's a little metal plate that only allows liquid to go through, and you put your material on there. We do this a lot with limonene, and then you put your dry ice and cap it. Once you get to, and you put this whole tube in warm water, not hot water, but warm, and once you get to a certain temperature, the dry ice is going to start boiling, but because of the cap being on, you'll develop a certain amount of pressure, so you'll increase the pressure while you're increasing the temperature, and we'll get to a point called a triple point. It's a point in which carbon dioxide is both a gas, a liquid, and a solid. And why I point that out is because normally we'll never see carbon dioxide as a liquid, but because at room temperature it can never be a liquid. But if you use enough pressure, it can become a liquid. And why is that important? Carbon dioxide is a non-polar liquid when it is a liquid, and it can help us extract our Carvone out, or limonene, or anything like that. So I mostly do this with limonene. We can also use GC mass spec with something called SPME. It's a solid phase extraction, and you would put your sample in a liquid, or just the sample itself if it's very volatile, and it injects a little fiber thing and then puts that into the mass spec, and then that gets absorbed into the mass spec and you can read it. The most common way you'll see analytical chemists extracting things is with these little cartridges, and you basically put the cartridges with the right solvents, and then you obtain the different materials. Another one is called socklet extraction. I'll talk about that in just a second, and sonification. So you guys, some of you might be choosing a project which is basically this lab, but you're going to be using sonification, and it's going to be a little water bath, but it's going to use sound waves, and that sound waves are going to generate bubbles, and then also because it's generating these bubbles, it's going to generate heat, and we're going to put our samples in these little vials or for your project, and you're going to compare it to this experiment to see is that any better. So sonification is another way of obtaining material. You can also do it with microwave, monowaves, and things like that. Socklet apparatuses are the more traditional way of doing these kinds of extractions. It's a little bit more intensive in terms of length of time, but it's basically taking a reflux, which is boiling the solvent, allowing it to go up into the socklet apparatus. That's what this thing is right here. And then once it goes into the socklet apparatus, it will condense back with the this condenser that you have, allowing it to keep going up and down, and your sample is right here. So it's basically allowing solvent to go through the sample multiple times, and it's like flushing it out of your material. But this requires heating, sometimes heating for days to do that. It's not a terribly harsh way of doing this, it's just more energy intensive. So we are going to be characterizing with IR, and you're going to compare the IR to using Spartan to generate a tentative looking IR. It's not going to be exact. And then you're going to use polarimetry and do some calculations. And then you're going to do refractive index and do some calculations. You'll compare your GC mass spec and your NMR. You're going to be looking for a couple of different things. You're going to be looking for carbon-oxygen bond, the carbonyl, which is around 1800-ish to 1700, but because it's next to another double bond, which is what we call conjugated, it may shift it to a slightly lower number. And we can use Spartan to give you a tentative value. You're going to be looking for carbon-carbon double bonds, not aromatic. These are not aromatic. And you're going to be looking for sp2 CHs and sp3 CHs.
And there's a little bit about the theory of that. But refractive index is basically a concept related to physics, where depending on the media that you're using, whether it's a solid or liquid, materials actually move light differently through different materials. And so with the refractive index, we can calculate what is the angle of incidence, like what degree does it shift light. And so the example that I have here is this pencil in the water. When you look at it, how light affects it is by making it look like it's changed position a little bit. So that is how light affects that material. You're going to be taking a sample, and it's going to be a pure sample of limonene, as pure as the bottle of limonene is. And there are two different instruments that we have. We have the Abbey refractometer, which is the much older version, or not original, but most commonly used version. So I want to show you, you basically look through here, and there's going to be a scale in there, and you're going to try to align the scale so that you get this perfectly straight line halfway through what you see in there. Then you switch it so that you can see a number, and that number is the angle refractive index. So it's basically looking at aligning your sample to the number, and then you adjust it to get it perfectly, and you read the number. Now, over the last many years, there's been more digital ones. And so I went and purchased 2 of these, which are also refractometers, but they're much simpler to use. It's pretty much like most of our other instruments. They're digital, so you put your sample in, it just reads it to you, rather than you having to play around and adjust this thing. So you'll see how to use that shortly. The polarimeter will... And before I forget, the refractometer, the number that you get back is a clue as to the evidence of a particular compound. It can also tell us kind of how clean the compound is. So the refractive index of a pure compound should always be the same, adjusted for temperature, that is, because there is a change depending on the temperature, and there's a calculation for that in your notebook. And in your ELN. The polarimeter, on the other hand, is going to help us distinguish one of 2 things. So with limonene, we have the R-limonene and the S-limonene. Both of those 2 things have identical characteristics. Their refractive index is the same, GC mass spec is the same, the IR is the same, NMR is the same. What they are different is how they interact with light in terms of moving light. Now, most of our other instruments can't detect that, but we have an instrument that can detect how it shifts the light around. So the basic idea of a polarimeter is that if you shine light through a sample, you just see the light, right? Now, if you... the problem is that light gets scattered by molecules very much. Specifically with chiral molecules, it shifts the light, but because light is already going in 1,000 different directions, what we have to do is to be able to measure this and this is what the polarimeter does. It puts a material or a film, or in some cases an electronic thing, that keeps light going in only one direction. So if light's going in all sorts of directions, how do you know which way, if light's moving in all sorts of directions, how it affected the light? So if you keep it one way, you can measure if it goes to one way or the other. So can it go to the right? Can it go to the left? And to how much does it do that? Enantiomers like R and S limonene will rotate light equally but in opposite directions. So if you don't know whether it's R or S, you can look up what the data is supposed to be. So limonene is recorded, what the R is and what the S is. And you can figure out whether the R is supposed to go to the negative side or the positive side, etc. We can't just look at a molecule and know that, and not every R is going to give you one direction, not every S. It really just depends on the molecule. Now, some of this data is already in your notebook for you. This data depends on the concentration of a solution, and so our instrument that we're going to use can actually do that calculation for us. But the original instrument, this polarimeter, this white thing right here, you would actually have to measure and then do the math yourself. The polarimeter that I've purchased for our lab is an automated one. We just have to tell it what the concentration is, and it will adjust our value. So this is the Autopol 1, and you basically are going to type in some information here. So you'll see that later. So once we get this information, we can do 2 things. We can identify what stereoisomer may be there, whether it's R or S. Now, if we had diastereomers, it could help, but it could be a little bit more complicated. But it could also help us if we have pure samples. And again, to determine which isomer is present, more likely, anyway, your sample just needs to be pure. Because if you have mixtures of stuff, you're going to get kind of different readings. It can also help us to determine if you have a mixture of the 2 enantiomers together in different ratios. It can help us determine how much of those. So there's a calculation for that. And so you'll see that in your lecture. but I also will have videos that can help you do that because you're going to need to.
Yeah. And there's a cap on there. You're going to suction, you need at least like 1 to 2 milliliters of liquid, because this thing holds about 1 full milliliter. So you're essentially going to do the same thing, fill it, and then you're going to check that it's filled. So it might squirt out a little bit on the top, and then check to make sure you don't see any air bubbles, because if you do, we're going to have to get air bubbles out. So then go ahead and put your sample in. In theory, I should have measured how much I put in there. We're going to pretend that I measured 5 grams in 100 milliliters of water. We're going to pretend. So you can close this again. And then you're going to click on this thing. I don't know what that symbol is, but it says scale. And then we want to tell it, we want it to give us the rotation value, but it depends on the concentration. So I need to tell it the concentration. So you're going to click on this thing, the specific rotation. You can click on the regular rotation, but then you'd have to do the math yourself. And if it will do the math for you, why'd you want to do it yourself? I don't know. Because your thing that you made is a solution, you click solution. Neat means there's no solvent, okay? Now I have to tell it what the concentration is. The cell that you have is the 50 millimeter one. It's short. There's a longer one, but that's a shorter one. Now we're going to put the concentration. So click on the little, this thing right here. Yes. And then we're going to tell it 15 grams. Because I said it was 15 grams in 100, it already says out of 100. So I'm just going to put 15. But let's 15.
50 or
15. There you go. Yeah. And just hit enter. Okay. Let's say that you didn't make it out of 100. I make it out of 100 because it's easy. But most of the time you're going to be making it out of like 10 or 200. Just multiply the grams. It's just an equivalence, right? So if you measured 1.5 grams in 10 milliliters, then it's 15 grams in 100, right? So go ahead and hit set. And then hit close, and then you're going to tell it to start. And then you back away from the instrument, because it's actually sensitive to vibration. Once it's done, and if I actually measured it right, which I didn't, it should give you pretty much close to what glucose should be, which I don't know what that is off the top of my head, but I can grab the bottle and find out. I have also seen that now we have our specific rotation. You just document that, right? And that's it. It does tell you what the temperature is, which is good. It tells you it's 21.9 degrees. But that's pretty much all you need.
In addition to your GC mass spec, which will be in your notebook, your IR, you're going to be running polarimetry, so you're going to need to dilute your sample according to the information. If you notice that your solution is a little cloudy, it's possible that you may have some impurities that are in your sample. And if there's any impurities in your sample, your solution might be cloudy. You may need to dilute it some more. Make sure you document how much you dilute it by, because you need that for the polarimeter. But you will also need to get TLC. And so when we run TLC is not perfect. Not everything shows up on TLC, but things that are going to be able to be seen on TLC will be your compound, and you may have some impurities that may also show up. So what you want to do is you take a little bit of your sample and dissolve it in either acetone. You can use ethyl acetate as well. You're going to take pure Carvone and dissolve it. And what you're going to do is you're going to spot your extract, And then you're going to take another micropipette and spot your Carvone, which you also need to dissolve in acetone. This is going to be your standard for comparison. And sometimes what people will do is run the Carvone and the extract on top of each other. And so what you're going to do is run it in the solvent, and you're going to document your RF values, and you're going to see, do you see just the one spot of the Carvone, or do you see other things? Now, there are some compounds that are going to probably be in your mixer that are not easy to see, and they may not be seen on the Carvone. The best way sometimes to identify them may be in using GC mass spec or NMR, mostly GC mass spec or liquid chromatography. And so in this regard, make sure that your samples are running up the plate and don't go over about a half a centimeter from the top, running up the plate straight. Sometimes we see students where their samples are going kind of lean, and then it's hard for you to determine anything. So once you've gotten your RF values, which you can review how to do that from Organic 1, you want to document that in your notebook. So again, you're going to be given the mass spec information, you're going to be given the IR information. What you need to collect is the polarimetry data, and you also need to collect your TLC data.